let me go over a few announcements first, and then we will, actually, I'll get to that, sort of peripheral to that question, but we'll get there. First, I want you to know, I can't remember if I announced this Tuesday or not because I just found out about it last Friday, so I may have forgotten to say it Tuesday. Normally on Fridays, I have office hours on the Birmingham West Campus from 8 till 12. Okay, 8 to 12 noon. Not tomorrow. I found out last Friday I've been assigned to go to Opelika to work on, for the state system, on some of the student learning outcomes, course description, that kind of stuff, for 2 courses that I teach, differential equations and linear algebra. Opelika. That's a long way. The meeting starts at 9 in Opelika. We are going to have to leave here around 6, maybe a little after 6. And the meeting goes 9 till 2, so I won't be back until somewhere around 5, coming in at rush hour. Who knows when we'll get in. I will not be on the Birmingham campus at all tomorrow, except right around 6 and right around 5. So if you want to get a little before 6, you can, or right around 5, you might, okay? But let me know if you are going to do that. Otherwise, I'll be out of there, okay? So that's the only time I'll be on Birmingham tomorrow. Now, sort of more bad news with this, I haven't gotten permission for this yet, but since rather than working 4 hours tomorrow, I will be working 11 hours tomorrow. I'm going to try to talk my way into getting next Friday off too, because I've got some things that we have to take care of. Great, right? Have to take care of, and the just tree business, and y'all can find out if you came in late what I'm talking about there. Yeah, it's doesn't look like much time to get things done. So I'm probably going to need next Friday as well, because I sure won't be able to do anything. See, normally Friday afternoons is a time for me to catch up on stuff like this. I'll be on the road or out, so I won't have tomorrow afternoon to work on this. So anyway, that's it. So that was the first major announcement. My office hours will not be there from 8 to 12 tomorrow at all. Not even close. Okay, now to address the question, let me make sure, was it Cormisha? Yeah. She asked about review, and I said that's what Have You Got Any Questions is about, so always have those ready. But I think I announced this back at the time of the syllabus, but I'm not sure everybody remembered or even that I remembered to say it, but let me make sure you understand now. And this is on the recorder. You can bring with you to every test we take in this class, including the final, a page of formula and equations. Whatever you want to write down on a piece of paper, you can have. So when we do have the test, which probably someone asked earlier, probably will be next week, either Tuesday or Thursday. I doubt if we're going to finish 1.9 today because I'm talking too much and got started late, but more than likely it's going to be Thursday, okay? So you can bring with you that, and that's a great review. That's better than me having a review because you are actively writing the stuff down, not just listening to me talk about it. Writing stuff down is much more active learning than listening to me talk about it, okay? So that's a great way to review. And if you have any questions from that, then I'll be glad to answer those as well. So start working on that this weekend maybe, right? Good deal. And that way you can ask questions you may have from it on Tuesday. And that also means I want to have all those quizzes in, okay? And right now, this class is really good about getting quizzes in. I still have 1, 2, 3, 4, 5, 6, 7 who have not turned in the first quiz. I'd love to get these back to you before the test, but I can't get them back to you until I get them all in. Now, you can always come by and see what you missed, but I can't return them to you until everybody turns them in. So please, if you haven't turned them in yet, get them to me today. You won't be able to get them to me tomorrow. Monday, that would be fine. And then, or bring them in Tuesday morning. Preferably before Tuesday. If I can get them all in by Tuesday, I want to return those papers to you. But if I don't have them all in, I can't return the papers. So, but remember this too. You cannot take the test until you turn in the quiz, with one exception. If you ask me politely to give you a 0 on the quiz, then I have to give you a 0 on the quiz, and then I can return it. You can take the test. Okay? I don't want to do that, but if you ask me politely, I can't say no. Okay? On that question anyway. Okay. All right. Any questions? Any other questions? Yeah. What's that?
Now, who in the world would ask you politely to give them 0?
I'm hoping nobody. Okay? So that means get your quiz is done. Okay, you've already done this. No.
Oh,
Okay. Well, I mean, they have said, I get to drop a test on it, I want to drop this one. You know, I've had that before. In other words, I'm giving them a 0 and I'm going to drop the test.
oh.
So I have had that, but, you know, I'd rather not. Okay, because quiz, actually, doing the quiz is a great way to study for at least half of the test, because that's the first 3 sections, 1.4, 5, and 6. Those are going to be on the test too. You get those, that's a great way to study for the test. And secondly, your quiz average can replace your lowest test score. So the higher your quiz average is, so please do the quiz, do well on it. Okay. Now, good points. Now, I believe this is where we left off last time. We were talking about inverse functions. Just someone quickly kind of explain to me what an inverse function does or undoes. If you have a function f, what the inverse function does is undo what f did. Okay? Remember the one we were talking about before? The function f was x plus 4. The inverse function was x minus 4. It undid what the function did. The function added 4 to whatever was inside. The inverse function subtracted 4 from whatever was inside. So in other words, when you form the composition of f with f inverse, remember when we did compositions, okay? We're still doing compositions. And remind me your name? Huh? Alexis. Good. Yeah. There you are. All right. Now, again, just to fill you in on what we're doing. We're in 1.9, the last section we're going to have before the test, which means I need the quizzes in before you can take the test. So please get the quizzes in as soon as possible. And you can have, on the test day, formula and equation sheet, anything you want to write down on a piece of paper to have with you. Okay. So remember when we did compositions of functions, we did f composed with g. Okay, you got another function. When you turned it around and did g composed with f, most of the time you got a totally different function. Remember, we did some exercises. And I know you did a bunch of homework exercises. Yeah, okay, good. Way to go. All right. And you remember, they never were the same. But, if you also remember, I said, except in a few very special cases. Here's that case. Okay? When you form the composition of f with f inverse, or the composition of f inverse with f, you always get the same thing. And that same thing is always the same thing. No matter what functions you have, you get the identity function, x. You get back, because guess what you're doing? F inverse is operating on x, doing something to it. F then operates on what you just did and undoes it, so you wind up with x again. Because this one takes x and does something with it, this one takes x and undoes it. So you wind up with x. Or you start with f for f of x, that does something to it, But then when you operate with F inverse, it undoes it, you wind back up with X. Both ways, every time, if you did the inverse function correctly. Okay? So that's what they mean. This is the one and probably only case where the composition works both ways. It does commute, and it always gives you X. All right, so here's example 1. Find the inverse function of f of x is equal to 4x. Okay? Does anyone want to make a guess about what that inverse function could be? Make a wild guess. Maybe an educated wild guess. Or just a guess. What could the inverse function be? Okay. Let me ask it this way. What does the f function do to the x? The f is operating on x. What does it do to it? What? What does the f function do to x? What's it doing to the x? Don't be shy. It's pretty obvious, hopefully. What does the f function do to the x? The f is operating on x. What does it do to x? Say again? Multiplies it by 4. All right, good. Brave souls here. Now, what might the inverse function of this be? Yes, by what? Exactly. That's my guess of what the inverse function is. Okay? Don't know for sure, but it's my best guess. Okay? Now, to check it, we verify by doing exactly what we were just talking about. Taking f of f inverse, and then turning around and taking f inverse of f. Remember when we did the composites? So let's do this one first. F of f inverse of x. Which do you plug in first? Say again? The innermost. Yeah, the f inverse. F of, and what is f inverse, or at least what we think it is? No. X over 4. Right? That's what our f inverse is. X over 4, right? X divided by 4. Now we take that with the f function. What does the f function do? Multiplies 4 times whatever's inside the parentheses, which is x over 4. And what do you get? 4x over 4, which is x. Ding, ding, ding. That's what we're supposed to get. Right? Now let's do it the other way. Let's do f inverse of f of x. Which one do we plug in first? The middle innermost function, so f inverse of, what is f of x? 4x. And then what does the inverse function do? It takes what's in the parentheses and divides by 4. So that'd be 4x divided by 4. And what does that give us? Ding, 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 x again. Perfect. We did guess well. That is the inverse function. Now that one's super simple, wasn't it? Okay? I think even I could have figured that one out. Okay? Now, there is a checkpoint. Please do the checkpoints as soon as you can after class. Okay, a few people still writing on this. Okay, let me clear the board and let's see how they did it. The function f multiplies each input by 4. To undo that, you need to divide each input by 4. And that's exactly what we did. we came up with the F inverse being, or at least our guess was, to be x divided by 4. Okay? Then, to check it, you verify that F of F inverse is equal to x. Well, F of F inverse is F of x over 4, because that's what F inverse was. And then the F function takes the number 4, multiplies it by what's in the parentheses, and that gives us 4 times x over 4, and that, of course, is indeed x. That's what we needed it to be. But we need to check it the other way and make sure it works both ways. So this time we'll take F inverse of F of x. Well, F of x is, from the beginning, 4x. Put that in there, and what does F inverse do? It takes what's in the parentheses and divides by 4. So that takes your 4x and divides by 4, and that is equal to x. So it does work both ways. This, and just about only this, is when the composite works both ways. And not only that, it always gives the same answer, okay, as any two inverse functions will. Any questions on that? Blah, blah, blah? Okay, never mind. Okay, don't answer that. All right. So let's look at the top of page 85, definition of inverse functions. We've been talking about them. Here we go. Let f and g be two functions such that f of g of x is equal to x. Okay? We think they may be inverses of each other. And this is true for every x in the domain of g. Okay? But we also know that g of f of x is equal to x, but these may be different x's because this is for every x in the domain of f. Okay? But guess what? If both of these are true, under these conditions, the function g is the inverse of f, and the function g is denoted by f inverse. Okay? F to the minus 1. That doesn't mean 1 over f. That means inverse function. And f of f inverse, which is what this is equal to x, and f inverse of f is equal to x. That's what we had here. The domain of the inner function f here must be equal to the range of f inverse. We knew that. The range of f must be equal to the domain of f inverse. Remember, when we first started, we exchanged x's and y's. It's swapping the domains and ranges. All right. Now, what I've been warning you about, they finally get the warning. Do not be confused by the use of the negative 1 as a superscript to denote the inverse function f inverse. That's what it means when this is a function. If that was a variable, x to the minus 1, that means 1 over x. If it was 7 to the minus 1, that means 1 over 7. That's what a superscript of minus 1 usually means, unless you have it associated with a function. Then it means inverse function. Okay, we use the same symbol for two different meanings depending on what it's with. Okay? In this text, whenever f inverse is written, it always refers to the inverse function. Okay? Not to the reciprocal of x, f of x. Okay? If the function g is the inverse of the function f, which we just had on the previous slide, then it must also be true that the function f is the inverse of function g. If it's inverse one way, it's got to be inverse the other way. For this reason, you can say that the functions f and g are inverse functions of each other. Okay? They still want you to check them both ways. Okay? So get used to that. All right. Now, okay, they're skipping example 2. Shame on them. Okay? So let's go back and do example 2. Which of the functions is the inverse function of f of x? Here's your f of x is equal to 5 over x minus 2. Okay? There's your function. Now, which of these two functions, g, the book calls it, okay, g of x equal x minus 2 over 5, or h of x, which is 5 over x plus 2. Now guess what? That last one we had, f of x is 4x, we knew exactly what the inverse was going to be, x over 4. That was simple. This is not so simple. So I can't look at that and tell you what the inverse is. It's not so simple. So which of those would you say is our best guess for being the inverse? G or H? G, okay? Let's check it. How do we verify that G is the inverse? We do f of G of x, okay? And which do we plug in first? The G of x, the innermost function. And what is G of x? X minus 2 over 5. That's an ugly looking 2, isn't it? Okay. Don't say anything, okay? Don't make fun of my writing, okay? Now, what does the F function tell you to do? Look up here at the F function. It says you start with 5 and divide it by whatever is inside the parentheses. In this case, it was x. In this case, it's x minus 2 over 5. And then from that, you subtract 2. So you see, that's what we've done. Okay? F of g, which is x minus 2 over 5, which you think may be the inverse, means you take the F function, which starts with 5, divides it by whatever's in parentheses, x minus 2 over 5, and then subtract 2 from it. Okay? Now, back in the day, probably when you were in, I'm guessing, Math 100 or so, they probably called this a complex fraction. I like to call it a complicated fraction, because it has a fraction in the fraction. Does anyone remember how you simplify that? Quick review. Find the least common denominator of all the denominators in the fraction. What's the only denominator you have here, here, and here? 5. So that's the least common denominator, right? Now what you do with that is multiply by 5 over 5. Okay, because what's 5 over 5? And when can you multiply by 1? Anytime you want to. It doesn't change the value in it, right? So we'll multiply the numerator by 5, and we'll multiply everything in the denominator by 5. I didn't write my 5 up here, okay? So this will give us 25 in the numerator, and in the denominator, this 5 will cancel that one out, giving you x minus 2, but then minus 5 times 2 is 10. So this gives us 25 over x minus 12. Does that look anything like x? Nope. G must not be the inverse. So scratch that. Okay? G won't work. Okay? Oops, I shouldn't have erased that. I'll come back and get it off. Okay? So what's our next guess of what might be the inverse? Anyone want to hazard a guess? H. Oh, good a guess. Okay, let's try H and see if it works. F of H of x. What's your H of x? 5 over x plus 2. So what does the F function do to that? It starts with 5 divided by whatever's in the parentheses. And what's that? 5 over x plus 2, and then subtracts 2 from it. Right? Okay. This time, I don't think I want to use that same policy of multiplying everything by the least common denominator. And the reason is, if I just remove these parentheses, which aren't really doing anything for me here, I just put them in so you can see what I was doing, notice what plus 2 and minus 2 add to. What is that? 0. So those disappear. So now we have 5 divided by 5 over x, right? That's what that line means. Let's write it this way. 5 divided by 5 over x. Don't you agree that's the same thing? Okay. Now how do we divide a fractional form? It's the same as 5 over 1, very good, times x over 5. And now what do we get? Ding, ding, x. Don't you like the sound effect? Ding, ding. Okay, they disappear. We got our x. I have a feeling h is your inverse function because it met the criteria that f of f inverse or f of h was equal to x. Now, how do we truly know that's true? Do it the other way and do h of f. If it is truly the inverse, then h of f of x should be x. Let's see if it is. Okay, which do we plug in first? The innermost function, which is f. So this will be h of, and what is your f function? 5 over x minus 2. And what does the h function do to things? There's the h function over here, hiding over here. What does it do? It starts with 5 and then divides by whatever is in the parentheses, which is 5 over x minus 2. I'm going to put it back in parentheses again. And then it adds 2 to that fraction, right? All right, a little on the messy side, but let's just deal with this fraction first. Can I take this and go up here with it? Okay? Let's do the same thing we did to this one, this fractional form. That's the same as 5 divided by 5 over x minus 2, right? Yay or nay? Okay. And then how do we do that? Hit it again, Sam. What would that be? 5. Say again. Over 1 times x minus 2 over 5. Now here's the trouble. I don't like to use that times sign. I'm going to make it a center dot because that looks like another x. Okay? That's why we came up with center dots. That means times 2. Okay? Now, what do you notice happens here? Don't the 5s go out? They've been dating. No, I'm just kidding. It was Valentine's. No, okay. All right. The 5 over 5 is 1, and that leaves this first term to be x minus 2, and the second term is plus 2, and what does that give us? X. Ding, 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 we got it again. Okay? So sure enough, h is the inverse of f. We verified it both ways. All right, good deal. Does that make any sense? All right. There's a checkpoint at the bottom of the page. Please do the checkpoints as soon as you can after class. Okay? Now we're ready for the graph of an inverse function. Okay? Now, I don't know if you'll find this surprising or not, but if you think about it, casually, you probably will see it. The graphs of f and its inverse, f inverse, okay, the function f and the inverse function f inverse, are related to each other. They're second cousins twice removed. No, okay. In the following way. Now remember this, if the point AB is a point on f, then what must be a point on f inverse? BA must be a point on f inverse. So that means that the graph of F inverse is a reflection across the identity function. Y is equal to X. We can draw that. That's just that diagonal line that goes through the first quadrant, also goes through the third quadrant, okay? And then if this is A units this way, okay, and B units that way, for this point AB, then take this B units here and move it down here. That'll be the X coordinate here. And let's take the A that was here and move it up here, and that's the Y value there. And sure enough, that's exactly equivalent across, reflection across that mirror at Y is equal to X. Now, let me point out a couple of things to you. Your F function here was always increasing. Your F inverse is also always increasing. So if F is always increasing, so is F inverse. If F inverse is always increasing, so is F. Okay? Because they mirror each other across the identity function. Okay? So here we have a nice way to do this. Now, if you really love graphing, do. Okay? If you do, maybe something's wrong with it, but no, it's perfectly fine, and you'll see they do look like this. Okay? Some of the others will be much more obvious. Okay? Now, here's example 3. Sketch the graphs, yay, of the inverse functions of f of x equal to 2x minus 3, and its f inverse is 1/2 of x plus 3. On the same rectangular coordinate system, and show that the graphs are reflections of each other across the line y is equal to x. So here will be your y coordinate, here will be your x coordinate. Okay, let's tick off a few points. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5. Positive 1, 2, 3, 4, 5. Negative 1, 2, 3, 4. Okay. How do we graph this function here? Anyone know a really easy way? What kind of function is that? Linear function. And what's the best way to do a linear function? What form is that in? Say again? What did you say? I heard something, but my hearing so bad.
Is it slope?
Slope intercept form. Excellent. Which is what? Say it again.
Y equals mx plus b.
Okay, yeah. So what is slope? What's intercept? Tell me. And that. Say again. -3 is what? The y-intercept. So it's actually a point, 0, -3. Where do I find that on the graph here? Say again. Go down 3. Is that what I heard? Say yes. All right, good. Good guess, okay? That's the point, 0, -3, right? That's the y-intercept, okay? I know what that tells me. What does the slope tell me? Okay. It is rise over run, right? So that means it goes up 2 for every 1 it goes to the right. Up 2 for every 1 to the right. That's what the slope means. Oops, I gave it away. I was going to ask what's the slope. Y'all knew, right? 2. So we'll go up 2 for every 1 to the right. There's another point. Up 2 more for every 1 to the right. There's another point. Up 2 more for every 1 to the right. There's another point. Up 2 more for every 1 to the right. And it's somewhere about like there. I can't see well. And I can't get any more. We could have gone down 2 for 1 to the left, but we can't get there. So let's just draw approximately what this curve is. It's a straight line. It's a linear function, right? Now, I really don't like the way they wrote F inverse here. Let's distribute the 1/2 across the parentheses. And what do you have? F inverse of x is equal to 1/2 x plus 3/2. Ooh, yuck. That's sort of messy, isn't it? Okay? Now, okay? Let's set this equal to y and see if we can make this look any better. Because your f inverse is just like f, it's equal to y. And multiply both sides by 2, and that gives us x plus 3 is equal to 2y. You see what I did there? All right. Now, why I did that, it's going to be easier to pick points now. Okay? For instance, give me, excuse me, I'm going to write this another way. X, subtract 3 from both sides, and you get x is equal to 2y minus 3. This time I'm going to say, give me a y. Rather than x, give me a y. 1, you said? Is that what you said? Okay, when you plug in a 1 here, what do you get? When y is equal to 1, what do you get for x? A negative 1, right? So there's a point right there. Okay? Give me another y. 0. What do you get for x? Negative 3. Okay, when y is 0, x is negative 3. That's over here, isn't it? Give me another, oh wait, that's all I needed, wasn't it? Okay, I just needed 1 point. Okay, here's why I needed 1 point. Let's go back to this form. Yeah, and the slope here is 1/2. So if we started with this point, that means up 1, right 2. And there's that point. And then we can just go from there. We don't have to do any more figuring. Up 1, right 2. Up 1, right 2. Up 1, right 2. Okay, something like that. Down 1, left 2. That would be over here. We could do maybe one more. Up 1, right 2. Something in there. Anyway, here is, oh, I should have done this in a different color. Give me another color. Say again? Blue. Carolina blue or regular blue? Regular blue. Okay, you're NC State. Okay, so here is the inverse function. I'm missing it up sort of badly. Something like that. My lines aren't very good. That's your inverse function. Now the question is that a reflection across the line y is equal to x? Y is equal to x is 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, negative 1, negative 1, negative 2, negative 2, negative 3, negative 3. There's a function y is equal to x. Is that a reflection? It sure sort of seems like it is. Okay? Yeah. It reflects across that axis. They're at the same point at 3, 3 because they're the same point. And then they reflect again up there. No. Say again? You said it's not a reflection, huh? Oh, yeah. You're making fun of my drawing, aren't you? That's what he's doing, okay? That just lost him 25 points on his final grade. No, I'm just kidding. Okay. Notice your F function is increasing. Your inverse F is also increasing. Yep, that seems to be it. Well, if you make fun of mine, I'll let you look at theirs, okay? All right. Oh, they just drew it like that, okay? And this looks just like mine, only smaller, okay? There's your F function going up like this. Here's your F inverse like this. And sure enough, perfect reflection across the identity function. It appears that the graphs are reflections of each other across the line y is equal to x. You can further verify the reflective properties by testing a few points on each graph. Well, look at them. Here is negative 1, negative 5. Here is negative 5. Right there, negative 1. These are every 2 here. Here is, we did this one, 0, negative 3, it was negative 3, 0. Sure enough, here's 1, 1, minus 1, here's minus 1, 1. Yeah, here's 2, 1, here's 1, no wait, 1, 2. Yeah, 3, 3, 3, 3. Same point, okay? Sure enough, that's reflection. Make sense? So, if you really have a hankering to graph, do this and you'll see, if you got them right, there will be reflections across the identity function. All right, that was example 3. Any questions on that? All right. Oh, here it says, note in the following list that the point AB is on, if that's on F, the point BA is on F inverse. What we just said. Minus 1, minus 5 on F, and minus 5, minus 1 on F inverse. And so on, and so on, and so on, and so on, and so on. Every point will be paired that way. All right. Now, they're skipping example 4. Oh, by the way, there was a checkpoint. Please do the checkpoints. Okay. Since we got started late, I have no idea of the time now. How we do it? Huh? 9:40. So we got 5 more minutes. Let's see if we can get example 4 done. Okay, that might be the best place to do it right here. Okay. Yuck. It's another graphic. Okay. Whoa. Come on. Okay. Verify graphically that the function f of x is equal to x squared. Now this has a caveat to it. Here x has to be greater than or equal to 0. We'll see why that is later. Okay? And g of x, which is the square root of x. Verify graphically that they are inverse functions of each other. Okay? And here's how I would suggest doing that. Oh, why did I do that? Remember, your x's have to be positive. So I don't need the line over here. I can put my y-axis over here because we're only going to deal with positive values. So we're going to be, in fact, since x's are always positive, you may not know this yet, but that means we're not going to have to deal with any y's being negative either. So there's going to be my x-axis down here. Okay? So let's first do f of x. Give me some points on f of x as long as x is greater than or equal to 0. Give me an x. 0, and what's the y? 0. Oh, let me check off a few points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Negative. Oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Oh, get back here. All right. So 0, 0. Give me another one. 1 what? 1, 1. Give me another one. 2 what? 4. Got it. Give me another one. Keep on going. 1, 2, 3. And what would be your y? Way up here. Okay, somewhere right about there. I can't go any further, so here is, what is that called? At least half of a parabola. Okay? Now, I want the g function in a different color. Give me a color. Help me. Green? I'm going to do dark green, okay? All right. Dark green. Give me an x. 0. And what's the y? The g? 0. Give me another x. 1. What's the y? 1. Oh, the same point. Give me another one. Give me another x. 4. Hey, I love that one, okay? What does your y? 2, right there. Give me another x. Yes. 5, 6, 7, 8, 9. And give me the y? 3. That's as far as we can go there. Here's what this one looks like. Okay? Now, the question is, does that seem like it reflects across What did you say? Yes, it reflects across the identity function. Y is equal to X. 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, 5. Yeah, perfect reflection. Because this was 0, 0, 0, 0, 1, 1, 1, 1, 2, 4, 4, 2, 3, 9, 9, 3. Yes, perfect reflection across the identity function. Okay, how about time? 43. That's just enough time for me to give you, to your delight, I'm sure, some homework exercises. Okay, I didn't want you to go away disappointed. We'll pick up next time with one-to-one functions, okay, top of page 87, and we only have a couple of pages to do. I think on Tuesday we will be able to finish 1.9, which means we'll be able to have the test on Thursday. Now, come armed with any questions you have. Use this weekend to your advantage to get studying for that test and bring any questions you have so we can have our review for any questions you may have then. But here's the homework exercises in 1.9. Any of the odds 7 through 13, they're all at Calc Chat, 9's at Calc View. Any either 15 or 17, both at Calc Chat, 15's at Calc View. Do 19, it's at Calc Chat. Do any of the odds 21 to 31, they're all at Calc Chat, 23's at Calc View. Do 33, it's at Calc Chat. 35 should be at Calc Chat. Okay, whoa. We'll stop there because we haven't talked about the horizontal line test yet. So we'll pick up the rest of those next time. Okay. Good deal. Have a good weekend. Of course, working on pre-calculus algebra will make it a good weekend, right? Yes. Okay. Sorry we lost some